We're going to have a Escher effect, I think. Does that, okay, so we have our quiz on Tuesday. Does anyone have any questions on that? Uh-oh. Yes.
Would it be possible to go over any questions on like homework 4?
I think we have some homework 4 like problems. At the end, we can see. Yep, there we go. Okay. Yeah, okay, so any other questions? Okay. So this one is functions and relations, which is, more relevant to your quiz. So on this one, we're going to be drawing the one set arrow diagram for the following relation R, where the domain and codomain is the set A equal to 0, 1, 2, 3, 4, 5, 6. And the rule is that x and y are in the relation if x plus y leaves a remainder of 0 or 4 upon division by 7. Right, so an example, 1 plus 6 equals 7, which has a remainder of 0. So that's in the relation, whereas 2 plus 3 equals 7. That does not equal 7, 5. And this does not have a remainder of 0 or 4. So this is not in the relation. So I'll give you about 2 minutes to do this yourself. Okay, so when I'm working on these, it's best just to go with just start with one element and then make sure that any pair is in the relation. So for 0, which element should I pair it with to be in the relation? Does anyone want to tell me? Oh, I don't have chat open. I'm really quiet? Okay. Okay, so we know that 0 plus 0 equals 0. That has a remainder of 0 when divided by 7. So that's in the relation. 0 and 1, that's 1, also not in, so that's not in the relation. 0 and 2 are not, 0 and 3. 0 and 4 is in the relation. And is 0 and 5 or 0, 6? Nope. So that's it for 0. Moving on to 1. Is 1 and 1 in the relation? Nope. 1 and 0? No. 1 and 2? No, that's 3. 1 and 3, that's 4. So that one is in the relation. 1 and 4 is 5. 1 and 5 is 6. 1 and 6 is 7. And then I'll just go faster. So 2 and 0 is 2, so no. 2 and 1 is 3, so no. 2 and 2 is 4, so yes, that is in the relation. 2 and 3 is 5, no. 2 and 4 is 6, that, nope. 2 and 5 is 7, which has a remainder of 0 when divided by 7, so that's in there. 2 and 6 is 8, which has a remainder of 1. 3 and 0 is 3. 3 and 1 is 4. So we can see that this relation is going to be symmetric, and that's because x plus y is commutative. We could have done y plus x. 3 and 2 are not. 3 and 4 are, because that's 7. 3 and 8. 3 and 5 is 8, which is not in there, and 3 and 6 is 9, which is not in the relation. And 3 plus 3 is 6, so it's not in the relation with itself. 4 and 0, yes. 4 and 1, that's 5, which is not. 4 and 2 is 6. 4 and 3 is 7, so that's in the relation. 4 and 4 is 8, which has a remainder of 1. That's not there. 4 and 5 is 9, which has a remainder of 2, so that's not there. 4 and 6 is 10, which has a remainder of 3, so that's not there. 5 and 0 is 5. 5 and 1 is 6. 5 and 2 is 7. 5 and 3 is 8. 5 and 4 is 9. 5 and 6 is 11, which has a remainder of 4. And 6 and 5 will also be there, and we've done almost all the pairs except we need to reverse that arrow. None of the other ones will work.
Wait, did you say when they're 11, it's a remainder of 4?
Yeah, so I can write 11 is equal to 7 plus 4, right? Right, so this says that, I can write 11 equals 7 times, 1 plus 4. So from our division theorem, this is 4. That's the remainder, right? Everyone good on that?
And why was 5? Itself?
5 I should not have done that. Thank you. Because 5 plus 5 is 10, which has a remainder of 3. So that was a mistake. Yeah, that's it. I have some device that keeps connecting and reconnecting. Anything else? Okay. Okay, so for this one, we're looking at the set of 1, 2, 3, and we're going to be thinking about the power set of that set. So remember, the power set is the set of all subsets of S. You can't hear Windows device connecting and disconnecting, can you? Okay. So we need to decide if the relation is reflexive, antisymmetric, or transitive. And if it fails, we need to give a property. If it fails, we need to give a specific counterexample to it being one of these properties. So can someone remind me of the definition of reflexive?
That means it can reference itself.
Yeah, so we have for every A in the power set of S, we need to show that A is in R. Okay, so if we come and look at the definition of our relation, we have two sets in the power set. And in order to be in the relation, their intersection needs to be empty. So does everything point to itself? It does not. Does anyone want to volunteer a counterexample to this?
I just have one question. Would it be for all A that exists in the power set of S times the power set of S?
No. Well, okay, yeah, but you would have to say all AA. So these two have to be the same because reflexivity is about equal elements. So you only need to consider one element at a time out of the power set. Does that make sense?
Okay, so for like vice versa, if we were to do B, so it'd be like for all B in the power set of S, B exists in R.
Yeah, but I mean, that's proved by showing that for every A in the power set, AA is in R. Does that help?
Yeah, that makes sense.
Okay. So, one of the elements here, I mean, maybe we should write the power set and maybe it'll become easier to see. So this is the two element subsets I'm writing right now. We are going to have 8 because the power set is 2 to the number of elements in the set. So this is 2 to the 3, which is 8. So just use that. If you're doing a power set problem, use that as a sanity check to make sure you've listed them all. So these are the one element subsets, and then we have the empty set down here. So if we take 1, 2 and intersect it with itself, then it's 1, 2, right? And that's equal to, well, A intersect A is equal to A, so this is 1, 2. So it does not have an empty intersection. So this is not reflexive. Everyone good on that? Yeah. Okay, so let's do antisymmetric. Can someone give me that definition?
If like A maps to B, then B doesn't map to A.
Right, if they are not the same element. So we allow, a self loop, right? So to put that more formally, we have for all A, B in the power set of S, if A, B is in the relation and A does not equal B, then BA is not in the relation. Does anyone have a guess on whether this is true or false?
I'm going to guess it's going to be true.
Why do you think it's going to be true?
I was just kind of looking at the power set, and if my logic is right, I don't see any 2 1s or 3 1s, anything that's not the opposite of anything currently.
Yeah. Okay. So
I'm going to say it's false because I'm looking at 1, 2, but I don't see 2, 1.
Yeah, so there's no 2 1s, then it can't be symmetric. If it's not symmetric, then it has to be anti-symmetric.
Your if it's anti-symmetric is a different property from being the opposite of symmetric.
Oh.
Yeah. So remember, you're going anti-symmetric. So we have reflexive, irreflexive. Both of those are not, you can't, proving one of those is false doesn't prove the other one is true. And we have symmetric and anti-symmetric. Proving it's not symmetric does not prove that it's anti-symmetric. So
I would say by the power set, since we have 1 pointing to 2 and 2 points to 3 and 1 points to 3. Wait, never mind. Wait.
What do you mean 1 points to 2? These are our power. These are our elements of our power set right here.
Yeah. So by timing them, don't we get like the flip of them basically?
Yeah. So basically, the question is there a way to do it? So I'll just give it to you. So if I say, like, let's just take 1, 2, 3 as A. And we intersect that with the empty set, that's equal to the empty set, right? And this is in the relate. So that means that the set 1, 2, 3 with the empty set is in the relation. But I could have also done empty set intersect 1, 2, 3. And that's also the empty set. So that means that BA is also in the relation, which falsifies this right here. Yeah. Any questions on that? Yeah, okay, so going with your example, if we took the set 1 and intersect that with 2, that's in the relation, right? No, that's equal to the empty set. So this is in the relation, but we could have flipped it around and gotten the same thing. So the reason this is failing is because intersection is commutative. Any questions on that?
I don't think I fully understand what is happening in the intersection. Like, why is empty set intersect 1, 2, 3 the empty set?
Yeah.
Right. Okay. So, where can I write this? Right. So remember the definition of the empty set, or the definition of intersection is equal to the set of X such that X is in A and X is in B, right? If we have A intersect the empty set, then we will never find anything that's in B here, right? So that means that I will never find an example for X here. So this has to be the empty set because there's nothing in common between the two. Does that help? Answer
yes. Yes. So because there's no common element between A and an empty set.
Yep. Correct.
The intersection is the empty set, or would you just say there is no intersection?
Actually, we have the. If you remember back to Theorem 6, we had the I forget what it's called. I think it's universal bound, where we say A intersect empty is empty. Right. We wrote it slightly differently. We wrote it as A intersect that thing.
Okay. And did this example with the empty set, did that prove that this was anti-symmetric?
This proved that it's not anti-symmetric because I showed that, for example, right here I'm showing that the set with 1 and the set with 2 are in the relation because their intersection is empty, and the set of with 2 and intersected with the set with 1 is also empty. So that means that I have A, B in the relation and B, A in the relation. Right? You just need to find one example where this doesn't happen.
Okay, and this does not prove it being symmetric because symmetric exists for all occasions.
Yes, we did not prove symmetry. We just gave an example of a symmetric of a element in the relation that is demonstrating the symmetry property, but that doesn't show that it's symmetric. Does that make sense?
Yeah, I wish I knew that a bit ago.
Yes, this makes sense. My last question, sorry, I'm asking a lot of questions. My last question is, why is the intersection of 1 and 2 the empty set? Or are you just saying that?
Yeah, so, right. So remember, it's the elements that are in both of them. 1 is not in 2, and 1 is not in this set here, right?
Right.
And 2 is not in this set, so there's nothing in common.
Right, but the empty set is in both.
Yes, the empty set is contained in both. It's not an element of both.
Good.
Okay.
I mean, even if the empty set is in both, it would be in the intersection, and so would be the intersection.
If the
since the NP set is in both, it would. I'm just saying, since there's nothing else, that's all you see is the empty set.
Yes.
So, I mean, if you want to think about it like that,
yeah,
you can.
That makes sense. That makes sense. Yeah.
Thank you. Anything else? Okay. And then finally, we're showing if this thing is transitive, and they did not give us enough room. Or maybe I took up too much room.
Do you have to show or just decide if it is?
Decide if it is.
So.
Yeah, so, well, okay, we have to give a specific example for why it fails if it fails. So if we remember, so every problem, just write down everything you know. So we know the definition of transitive is that for all A, B, and C, am I writing too small? I don't know how to add a page to this on the fly. Nope. Maybe I can. I don't know. So for all A, B, and C in the power set of S, if A and B are in the relation, yeah, I'm seeing the answer in chat, and B and C is in the relation, we need to show that A, C is in the relation. So I'll give you 2 minutes to think about that. So think about whether it's true or false. Maybe just 1 minute. Okay, so if someone wants to yell something out, I'll do that, or I'll just go with what's in chat.
Isn't this true because we have one, just the the set 1, 2, which is AB, and then we have the set 2, 3, which is BC, and then we have AC, which is 1, 3.
Okay, so I think there's a slight confusion here. The elements of the relation are pairs of sets. The sets themselves are not part of the relation.
So the numbers in the set don't relate to whether or not it exists in the set or in the relation.
Right.
Okay.
So like I could say this A is equal to this one, element B is equal to this one. Yeah, so I'm seeing some counterexamples in the chat. I'm going to go with Mohammed's because it's the easiest one. So we have the pair with the set 1 and the set 2, 3. So is this in the relation? Yes, because they have an empty intersection. So I'm going to say A equals this. B equals, or not B. A equals this. So now for our middle element, we're going to have B equal to 2, 3. And for C, we're going to have the set 1. So it's going to be the same as A. So as we discussed earlier, because intersection is commutative, both of these pairs are in the set, the relation. So if we look, we're going to have to require that AC is in the relation. Well, AC in this case, so A is 1, the set with 1 in it, and C is the set with 1 in it. This is not in the relation because the set with 1 intersect the set with 1 is equal to the set with 1. So we demonstrated that transitivity does not hold. Does that make sense?
What would have to be different for this proof to not work?
What do you mean?
Like, is there a version of this where you could have 1, 1 in the relation?
Yeah. Okay, so we could just, so is there a version, you're asking, is there a version of this problem where this works?
Right, where A is 1 and C is 1, and then AC 1, 1 also exists in the relation.
You could make, so you could just have self arrows on everything. That will work to make this a relation and a transitive, because there's nothing to show there.
So it's not transitive because it's not reflexive.
It's not transitive because it's not reflexive.
Or is it just happens to be both?
You can be transitive without being reflexive.
But if you're not
this one is failing for the same reason it's not reflexive though.
Okay.
Right. So if I have that, that's transitive but not reflexive. Is that right? I really wish we had a second page on this one. Hopefully the video, you can see how it all happened. Anything else? Okay. Yeah. So we're doing this because your quiz is on Tuesday, so we want you to get some extra stuff in. So we're going to have a transitive relation R on a set A, and we need to show that R inverse is transitive on A. So let's just begin by writing down what we know. So for transitive, we know that that means for all A, B, C, and A, B being in the relation, B, C in the relation implies AC is in the relation. And does someone want to remind me of what our inverse means? So our inverse flips the arrows around, right? So if I had this as my relation, so if this were our inverse would look like this. So this is equal to the set A, B, in A product A, such that BA is in R. So that's the definition of inverse. And I'll give you, I think, 3 minutes to work on this. Another question I have is, do people like breakout rooms?
I like.
You like them? Okay, do we want to try a breakout room?
I like them.
Okay, I'm getting a lot of, yeah, okay. I mean, if you don't want to participate, you don't have to. So we'll do this for, yeah, a few minutes. For 3 minutes, I guess. Ah. I don't know how to do this. Let's forget it. Yeah, so maybe we'll try breakout rooms next time. But okay, has anyone made any progress on this? Okay, so maybe you can help me along as we get going. So we're trying to show that our inverse is a transitive relation. So what we need to show is that for all x, y, and z in our set A, if, not A, yeah, you have the right idea in chat. So if x and y is in our inverse, and y and z are in our inverse, we need to show that x and z is in our inverse. Okay? So if we look here, we can say, okay, if x and y are, if xy is in our inverse, then that means by the definition of the inverse relation, xy in our inverse means that y comma x is in the relation r by inverse, and y and z being in our inverse implies that zy is in the relation, and that's also by inverse. So remember, we're trying to find x and z in our inverse. And the only thing we haven't used yet is the fact that this is symmetric. So does anyone know how to finish this?
How do we know it's symmetric?
That was not symmetric, I'm sorry, transitive. We haven't used the fact that it's that R is transitive.
So could we say that y comma or x comma z or x comma z exists in R by definition of transitive, and then take the inverse of that?
Yeah. So that's close. So we see we have this middle element right here, right? So we have zy from here and yx both in R. And by transitivity, we can say that xz is in R, not xz, zx. Zx is in R. And if we look at this, okay, so this is in R by the definition of the inverse relation. So by the inverse relation, we conclude that xz is in R inverse. And that demonstrates that this that R inverse is transitive.
Does the order of the steps matter? Can I just start and say, since we know R is transitive, we have x, we have z, like we have xy, xy and yz and x and
yeah, you could write this backwards.
I mean, that's yeah.
If that makes more sense to you, that's. I mean, that definitely do it.
Do
Do it in the way that you're most comfortable.
Okay, I just wanted to make sure. There's multiple ways to prove the same thing. Good.
There are. Yep. I've seen tons of ways to do it. Hope that if you do it a different way, it's right. That's a lot easier for me to grade. Yep. Okay, so any more questions on that? I am trying to write these more like what we would expect your proof to look like. Okay, next one. This one's fun. You're not going to be doing something like this on the quiz. You're not going to be doing crazy math like this, but it does demonstrate some important things. So, so we have our function f of x from the reals to the reals, and we are deciding if it's one-to-one and onto. And if either property holds, we need to give an example to explain why. So I'll give you 3 minutes to think about. Well, actually, okay, let's do 1 minute to think about one-to-one. What's this? Okay, does anyone know if this is one-to-one? Yeah, okay. 1-to-1. So Mohammed says that it's not one-to-one, and his counterexample is that, so if we take f of 0, let me make sure I have room, okay. F of 0 equals 0 squared plus 0, 4 times 0 plus 1, that's equal to 1. And f of minus 4 is equal to 16, which is negative 4 squared, minus 16 plus 1, and that's equal to 1. How did you find that? Yeah, okay, so, okay, someone's prepared. So the way I would do this is I would say, okay, well, let's just hope that we can find something easy. So I'm going to say x equals 0. So if I plug this in, I get x squared plus 4x plus 1 equals 1, right? And nope. Yeah. Equals, we're going to try to solve this equation. So, yeah, we do, so this is equal to, we're going to set these equal, 0 squared plus 4 times 0 plus 1, and that's equal to 1. So we take x squared plus 4x plus 1 equals 1, and subtract 1 from both sides. And I get x squared plus 4x equals 0. And then we can factor out an x. We get x plus 4 equals 0. So our two choices here. So this one says that x equals 0 is a root of this expression here. And minus 4 is, x equals minus 4 is also a root from this one right here. Yep, and you can use the quadratic formula, and that's why I have it written. But, you know, if you can factor it, that's also fine. We'll do the quadratic formula for the onto. So is everyone good with that? I mean, a lot of this is just being lucky to find something. So we're going to do onto x squared plus 4x plus 1. I'm doing onto. Would it help to complete the square first? I can't remember how to complete the square. it might.
Don't you just use like the quadratic formula to complete the square? If you can't see it automatically.
Yeah. Right. So first, do we think that, okay, yeah. That is the correct completing the square. So Caden has x plus 2 squared minus 3. Yeah. So Sam has noticed the critical problem here. And in fact, so we got the answer that this is not onto. And I had this plot up here. If we look at the graph, yes, there's nothing below minus 3. So I'm going to use the quadratic formula here. Nope. Negative b plus or minus square root of b squared minus 4ac all over 2a. And so let's say that we want to solve this for negative 4. So we would get x squared plus 4x. So solve for f of x equals minus 4. X squared plus 4x plus 1 equals minus 4. So we're doing x squared plus 4x minus 3. Nope. If I can do math, that would help. Plus 5, because that's minus, is equal to 0. So if we go into our quadratic formula, we get minus 4 plus or minus the square root of 4 squared minus 4 times 1 times 5 all over 2 times 1. And we get minus 4 plus or minus the square root of 16 minus 4 times 1 times 5 is 20 all over 2. And if you remember from middle school, I guess that's when they teach it, this is a bad sign here because we need to take the square root of 16 minus 20, which is the square root of minus 4, and this is not a real number. So this is telling us that we can't get minus 4. Is everyone good with that? Questions on that?
So the definition of onto.
Oh,
if
yeah.
It was like, how does this? So what's the definition of onto then?
Yes. So good question. So for all y in the codomain R, we need to show that there exists an x in the domain R such that f of x equals y. So that's the definition of onto. That is not the definition on. Yeah, that is the definition of onto, right? So if you think about it, you have your points in your codomain. You need to have arrows coming into every element to be onto. Does that help?
So any even polynomial wouldn't be onto then.
Yeah. Yeah, and it happens because you're never going to get, right? So if we look back here, even polynomials are not going to have, they're going to go to positive infinity on both sides. They're never going to go to negative infinity. Yep. So that's the right intuition. Any other questions?
Is there be a problem like this on the quiz?
No. You're not going to be, it's not going to be.
We won't have to go through this nightmare of quadratic formula?
You're not going to use the quadratic formula on the quiz. I can guarantee that.
Okay, great.
You are not going to require a calculator either. On either of any of the remaining exams, a calculator will not be required. Anything else? Okay. So this one is the function from the set 1 to infinity that maps to the set 1 to infinity. And it has the rule f of x equals x divided by x minus 1. And we need to prove that f is 1-to-1 and onto. And we need to find the inverse function of f. So which one do we want to do first? 1-to-1 or onto? Oh, we're almost out of time. We are out of time. So let's do 1-to-1, write the definition of that. So for all y in 1 to infinity, we need to show that there exists a, that is not 1-to-1, I'm writing onto. So for all x comma y in 1 to infinity, if f of x equals f of y, then we need to show that x equals y. I'll just start on that because we're very low on time. So we'll just start with, we're just given an x and y. So given x, y in 1 to infinity, we know that f of x equals f of y, so we can go and apply the definition. So f of x equals x divided by x minus 1, x minus 1, and that is equal to f of y, which is y over y minus 1, f of y. So here we can do a cross multiplication. So we'll multiply both sides by, we'll multiply the right side. We'll multiply both sides by y minus 1, and we get y minus 1 times x equals y. That's over x minus 1. And then that means that y minus 1 times x equals y times x minus 1. And then if we distribute these out, we get yx minus x equals yx minus y. We see that the yx's cancel on both sides. And that means we have negative x equals negative y. We multiply both sides by minus 1. And that means that x equals y. So we've now concluded that x equals y. And that shows it's 1-to-1. Yeah. Any questions on that? Comments? Any last questions before? Do we want to see the onto one? That one's more involved. Okay, I think we'll call it there. I don't know how far other TAs got into it, so you can work on it on your own or watch it on our live streams on YouTube. Unless you want me to, I'll just do it. So f of x equals x over x minus 1. And we're showing onto, which means to show that for all y in 1 to infinity, there exists an x such that in 1 to infinity, such that f of x equals y. So we're just going to be doing this backwards. So y equals x over x minus 1. And so we get y times x minus 1. So what we're trying to do is solve for x. Solve for x. So y times x minus 1 equals x. That means that yx minus y equals x. And then we can factor, we can move this over here. So we get minus y equals x minus y, x. And then we can factor out the x. Minus y equals x 1 minus y times x. And that means that x equals, when we divide by 1 minus y over 1 minus y. Or alternatively, you could write this as y over y minus 1 if you multiply both top and bottom by minus 1.
Would that make the x negative if you have to multiply everything by negative y?
Would it make what? Yeah, so I did minus 1
So
times
did you
minus.
get there by substituting the x to be xy minus y at the very last step and simplifying?
Very last step.
Or
Okay, yeah, the very last step, I multiplied the top and bottom by minus 1. So this becomes plus 1. This is plus 1, and this is
then
minus 1.
I just am confused how you went from negative y equals 1 minus y times x to x equals y over 1 plus y. Because I thought we built that x equals
Where are we
yx
looking?
minus y. Have x equals yx minus y, and you have x equals y over
X
1.
equal, where? Can you tell me the step number?
So there's step two where you
Right
have
here?
Yes, that one, and then the step where you have x equals negative 1 times y over...
Okay, so how did I get to this step?
No, I'm just confused. Like, that makes sense. I'm confused how you went from negative y equals the quantity 1 minus y times x to just the next step.
This step or this step?
I don't know how to say.
Okay, I'll just walk through it. Okay, so here we distributed the y across, and we really need to finish. And then I subtracted yx from both sides, right? So that's how I got to here. And then right here, we have minus y equals 1 minus y times x. And this is because I factored the x out right here to the right-hand side. I could have written it that way. And then I divided both sides by 1 minus y to get, okay. So then I would have minus y over 1 minus y equals x. And then when I flipped it around, I would get this. Yeah.
That makes more sense. Okay, I just got confused.
I'm sorry, I skipped a step there. I'm sorry. And I think we are definitely out of time. So thanks, everyone.
Thank you so much, Mort, for sticking through and answering all of our many questions.
Yep, no problem. Is Lynn in?